Hello, I'm Mr. Craig, and I want to work out the examples for balancing chemical equations. So let's go ahead and go right to it. Alright, so looking at the first example, probably the best way, essentially since we're starting out for our first time of balancing chemical equations, is to do what's called the inventory method. So what that means is I want to write down all the elements that are on the reactant side, and also write down all the products. So it doesn't matter what order, but I like to keep them in the same order when doing this. So I have my aluminum, I have chlorine, I have barium, I have nitrogen, and oxygen. So those are the 5 elements that are on the reactant side. I'm going to do the same thing on this side. I'm going to go in the same order, put aluminum, chlorine, barium, nitrogen, and oxygen. And what I want to do is now count up and see how many of each of these I have. So on the left side I have 1 aluminum, I have 3 chlorines, that's what the subscript means, I have 1 barium, I have 2 nitrogens, since I have the parentheses here, the nitrate, and there's 2 of those, so that means I have a total of 2 nitrogens. My oxygen I have 3, but I need to multiply that by 2, so initially I start off with 6 oxygens. Go to the other side. I look at how many aluminums. I have 1. Chlorine, I have 2. Barium, I have 1. Nitrogen, I have 3. Oxygen, I have 3 times 3, which is 9. When these numbers are the same on both sides, the reactant and the product side, we are balanced. Initially looking at this, these numbers are not the same. So the chlorines are different, the nitrogens are different, and the oxygens are different. Okay. As a heads up, what I like to do, or a good rule that I found, is try to save the oxygen and hydrogens for last. Just try to save those for last. So if you see those like in somewhere in the order, like if we had oxygen listed first, save it for last, because you'll notice that oxygen appears in a lot of things, hydrogen will appear in a lot of things. We don't have any hydrogen in this case, but we definitely want to save the oxygen for balancing for last. And that'll make a lot more sense once we start doing some combustion reactions. So first thing, doesn't matter where you start, aluminum, and make sure you do this in pencil and have a big eraser standing by, because again, when starting out looking at how to balance these equations, you're going to make some mistakes, you're going to erase. And what we're trying to do is, we never ever want to change these things here. These are locked in. These are your chemical equations. They're balanced out, they're ready to go. So we never want to change these. What we're going to do is, we're actually going to put what's called a coefficient in front of those. So if I have, say, like a coefficient of 4, what that means is I have 4 barium nitrate molecules. If I have this 4 in front of the aluminum chloride, that means I have 4 aluminum chlorides. So essentially what that means is I'm going to have 4 aluminums and 12 chlorines. That's if that's the number that I'm going to have, which I seriously doubt it. So let's go ahead and get started here. So aluminum looks good, so don't mess with it. Now that doesn't mean that we won't change it, but for right now we're looking good, so we don't want to change it. Looking at chlorine. Chlorine is in this compound and this compound, but we don't have the same numbers on both sides. What we have to do when we write a coefficient is that we have to use what's called a whole number. We can't use fractions in these. We don't have a fraction of a molecule, so we have to have whole molecules or whole numbers in this. So the only way that I can resolve getting these to equal the same is find a common denominator or a common value. So if I have 3 and 2, well, I'm going to multiply this by 2 and multiply that by 3. And the way I do that is I put a 2 there and a 3 there. Now, what I've just done is I've balanced my chlorines. So to check, I have 2 times 3, which is 6. And then I have 3 times 2, which is 6. Now, since I put a coefficient in front of these, I need to actually balance those as well. So now I've got 2 aluminums. I'm going to update that. And I have 3 barium, and there I go. Okay, so again, the inventory method is to help you keep track of what's going on here. Now, what we don't do, and you might find out later on, you might want to try this, is like, oh, if I put a 3 there, I've already got 1 barium, so that means I have a total of 4. No, it's how many you have after you put the coefficient in. All right, so let's go right back to the aluminum. Since I have 2 here and only 1 there, let's go ahead and put a 2 here. That'll give me 2 aluminums. Now it also changes my nitrogen and my oxygen, so let's update those values. So if I have 1 times 3 times 2, so 1 times 3 is 3 times 2, that means I have 6 nitrogen. And how many oxygens do I currently have? I have 3 times 3 is 9 times 2, which is 18. Okay, so that's my current inventory. So when I look, my aluminums look good, my chlorines look good, my barium does not look good. So since I have a 3 here, I need a 3 for my barium. So I'm going to put a 3 there. That gives me 3 barium. Now let's look at our nitrogen, since that affects that as well. So we have 1 times 2 times 3. So 1 times 2 is 2. 2 times 3 is 6. So I have 6 of those. Now let's do our oxygen. We have 3 times 2, which is 6, times 3 is 18. Okay, so when those numbers are the same, and they are, we're balanced. So again, this will get a lot faster for you. But until you are super fast, and I hate to say it, but these are actually the easier ones to balance, and I'll show you a trick in the next video. All right, so let's look at number 2. These are probably the most difficult to balance. I'm not going to lie when I say that, but these are the most difficult to balance. These are called combustion reactions. Let's see if I can spread that out a little. Okay. When we have combustion reactions, all the combustion reactions where we have oxygen, and that's what qualifies for a combustion reaction. We have oxygen burning something. And in this case, when we have a carbon with a hydrogen molecule, your products will always be carbon dioxide and water. Same stuff that you're breathing out. You are undergoing combustion reactions in your own body. Just don't realize it. If you're not sure, check your forehead. It's pretty warm. So same thing, let's do a inventory. So we have carbon, hydrogen, and oxygen. And on this side, we also have carbon. Let's keep it in the same order, hydrogen and oxygen. And let's find out how many we have. We have 5 carbon. We have 10 hydrogen. And we currently have 2 oxygen. That'll change. Over here we have 1 carbon, 2 hydrogen, and now notice that we have oxygen in both of these, so you have to keep track of the oxygen, all of the oxygen atoms, or all of the carbon atoms, or all of the hydrogen atoms on the same side. So in this case we have 2 plus 1, which is 3. Now, when working these types of problems out, and I'm going to be very, very straightforward with you. These are the hardest ones to balance, but if you remember these 2 rules, actually these 3 rules, these combustion reactions will turn out to be the easiest. First one, try to make that an even coefficient. Okay, try to make that an even coefficient. Also, try to start balancing this one first. Okay? Balance the water or balance the hydrogens first if you can. In some cases you can't, but in some cases you can. Now, if we have, say, the reason why we want this to be an even value is because a lot of these combustion reactions have an even number of oxygen atoms. Notice that there's no oxygen on this compound, but if I put an odd number here, that makes an odd number of oxygen, and there's no way I can balance it. So make it an even coefficient, balance the hydrogens first. Okay? Just saying. And then the last thing, so that's the first step, there's the second step. We want to balance this last. Okay? Save the oxygen for absolute last. Don't try to balance the oxygen second or third. Save it for last. Trust me on this. Okay? So there's your hints. Now I'm going to leave those little hints up there to help us. So what that means is I'm skipping the carbon. I'm going to go right to the hydrogen. And in this case here, since I have my hydrogen, I should use that color. If I have 10 hydrogen over here and I want to get 10 over here, we might say, oh yeah, let's put a 5 there. But what have we just done? We put an odd number there. So if I have an odd number here, that means I'm going to have an odd number on this side, and there's no way I'm going to be able to balance it. So I don't want an odd number. I want an even number that is divisible by 5. So whenever you see something like that, just multiply it by 2. So 5 times 2 is 10. Trust me. That one step right there, or those 2 steps right there, are going to save you so much time when balancing these combustion reactions. All right, so let's do our inventory count here. So I've got 10 times 2, which is 20 hydrogen. So let's count up our oxygen. So we have 10 times 1 plus 2. So that is, what is that, 12. Okay. So let's go to the other side, and let's balance the hydrogen over here. So that means I need to put a 2 in front of there to balance the hydrogen. So what that means is now I have 20 hydrogen, but I also have changed my carbons. So 2 times 5 is now 10. Okay. All right, so we don't want to try to balance the oxygen, so let's balance our carbons. So if I have 10 on this side and I only have 1 over here, then I need to put a 10 there. Again, this gets a lot faster. So now I have 10 carbon. So I've changed my oxygen count. So I have 10 times 2, which is 20. But don't forget, you have 10 times 1 over here. So 10 times 2 is 20 plus 10 times 1, which is 30. Okay. My carbons look good. My hydrogens look good. So I'm going to now balance my oxygen, which is the only thing that isn't balanced. And so if I need to get 30 oxygens on this side, what do? Well, I have a 2 here, so that means I need to take 30 divided by 2, which is, that's right, 15. And that will give me 15 times 2 is 30. So in this case, now my carbons, hydrogens, and oxygens are balanced. And the reason why I did not have to erase anything in this case on these very difficult combustion reactions is because I started with my water first. I made my coefficient for the water an even value, and I saved my oxygen for last. Now, one thing that we always have to do, regardless of how simple or how difficult these are, is always ask yourself, can these coefficients be simplified or reduced? When I look at the first problem, I can't reduce that. When I look at the next problem, is it possible to reduce this? In other words, I have 2, 15. No, these numbers are not divisible by each other. So if that were a 3, if that were a 5, I could reduce it down because they'd all be divisible by 5. But in this case, we cannot. So this is the lowest coefficient value that we have here, or lowest whole number ratio. That's even a better term. All right, example number 3. Looking at this one. We talked about polyatomics earlier on in the year, and in some cases it's really nice, and we'll talk about this type of reaction a little bit later on. This is actually called a single replacement reaction. And what that means is that the metal is going to kick this metal out. And you'll notice that that takes the place of that, and then the copper is all by itself. That's a couple days from now, so let's not worry about that. That's a single replacement reaction. However, we do have something pretty cool here, which is a phosphate. In other words, that phosphate doesn't change from this side to the next side. Okay? And whenever you see these polyatomics that don't change, in other words, I have PO4 here, and I have PO4 here. Now you'll notice that, yeah, I got my parentheses here that says I have 2 of them, but that's okay, I can live with that. That's kind of cool. So whenever you have a polyatomic, think about polyatomics as a single element. If it doesn't change, notice that there's no oxygen here, no oxygen here. So we can think about that. Now, if you're not comfortable with that and you still want to do this, that's fine, but this is a shortcut. Okay, so when I do this, what I'm going to do is I'm going to write down these things. I'm going to have iron, I'm going to have copper, and I'm going to have phosphate. Okay, I'm not going to put the charge on the phosphate since you can't see it. Do the same thing over here. I'll have iron, I'll have copper, I'll have phosphate. Okay, and notice that the PO4s don't change from here to here. There's still -3 on both sides, but my inventory gets kind of fun. Okay, in this case here, how many irons do I have? 1. How many copper? 3. How many phosphate on this side? 2. So I put a 2 there. Come over to this side. How many iron? 1. How many copper? 1. How many phosphate? Just 1. There's no parentheses. Okay. So now that I have that, and you don't see any oxygen, so we don't have to worry about saving that for last. Irons look good. Don't mess with it. Copper, that's a problem. We have 3 here, but we only have 1 here. So if we put a 3 there, that makes it nice and tidy. And then I have 2 phosphates here and 1 phosphate over here. So if I put a 2 here, okay, now that means I have 2 phosphates, but it does change my iron count, which is okay, because now I have 2 there. And then when I look at that, I say my phosphates look good, my copper looks good, but my iron doesn't. We're done. Now, if you don't feel good about leaving that blank and you want to put a 1 there, that's okay. But it's also okay if you don't put a 1 there. It's if we have at least one thing showing here, it's understood that that 1 is present. Okay. But if you just initially, when you're working these out for the first time, you're like, I don't feel good about having nothing there, then you could put a 1 there. But in the future, we'll get rid of that. We won't show that. But this works out great. And again, the same thing would happen as if you worked it out and you had your phosphorus and your oxygens. We'd still get a 2, 2, 3, or a 2, 1, 2, 3. If you don't believe me, try it out. All right, let's look at the last example. Okay. Here we have another combustion reaction, but we're not going to be freaking out because these numbers are ridiculous. Not a problem. Do the same thing we've been doing. Again, do your inventory. So I've got our carbon, hydrogen, oxygen. On this side, carbon, hydrogen, oxygen. Same thing. Don't worry about the order in which you put it in here, but do worry about the order that you work it out there. Because again, we want to try to do this system where we're going to balance the waters first and make it an even value, and then we'll save the oxygen for last. Just a good habit to get into. All right, so let's write down what we know. We have 12 carbons, we have 22 hydrogens on this side, and we have 5 oxygen. Okay, looking on this side, 1 carbon, we have 2 hydrogen, and we have 3 oxygen. Okay. Are those numbers the same? No, not even close. So again, balance this first, make it an even coefficient. And again, if we have to reduce, we can reduce. It's fine. And then save the oxygen for last. So we have 22 hydrogen over here. How can we get 22 over here? Well, if you put an 11 there, that's an odd number. Not going to be a good value to have there. So take that 11 and double it. And let's make it a 22. Okay. So now that gives us 44 hydrogen. Okay. And let's get our oxygen count. So we have 22 times 1 plus 2, which is 24. Okay. So let's come over here, balance our hydrogen. So we have 22. That means we need to have a 2 there. That gives us 44 of those. And let's balance our oxygen. So we have 2 times 3, which is 6, plus 2, which is 8. And also affects our carbon. So 2 times 12 is 24. Okay. Hydrogen's looking good, so we need to balance our carbons. So to get 24 of those, we need a 24 there. So 24 carbon. 24 times 2 is 48, plus 22, so 48 and 22, what is that, 60? I believe, no, it's 70. So we have 70 oxygen. Okay. And let's see, our carbons look good, our hydrogens look good. So we need a total of 70 hydrogen on this side. So we need 70 hydrogen. However, we already have 6. Don't forget about the hidden elements sometimes that are in here. So we have to subtract 6, and that gives me 64. And then 64 divided by 2 is a 32. And that gives me a total of 70 oxygen on this side. Now, those numbers look great, but can they be reduced? When I look at this, I'm like, I think these can be reduced. They're all divisible by 2. So once you have this, don't erase those numbers. Simply reduce it. So that is what? 16, hang on, 12, and 11. Okay. So when working these out, again, there's a couple ways. There's more than one way to balance chemical equations. In the end, we want to make sure that the number of atoms are the same on both sides when we finish. Do you have to show this method? No, but it's going to be very, very helpful if you do. And again, when working out these types of problems, there's nothing wrong with doing it the first way that we worked it out. So you can show individual atoms, or if you have a polyatomic, that doesn't change. In other words, if this goes from PO4 to PO3, you can't say that these are the same. All right. So if you need extra help on the homework, I am going to make a video about the evens here in a moment. So I hope this was helpful.